Hello, I'm Jakub Opashal, and I would like to talk about this paper with Venkat Kuriswamy and Sai Sandeep. So the paper is about alphabet reduction in Dinurs Proof of the PCP theorem. I will very slowly explain what either of those terms mean, starting with the PCP theorem. So the PCP in the PCP theorem stands for probabilistically checkable proofs. It refers to the original phrasing of the theorem, which is an alternative characterization of the class NP. You probably are familiar with the characterization of the class via polynomial-sized proofs. So this PCP theorem actually says that there are proofs that are not only polynomial-sized, but they can be checked with some level of certainty by looking only at small bits, a small part of the proof. So this theorem was discovered by Aurora and Safra in 1998. The formal statement looks like this. It states that there is a universal constant epsilon, such that any language in NP has a verifier that verifies a proof that reads only 3 bits from the proof. These 3 bits are chosen at random via some random distribution that the verifier can choose, such that it satisfies these 2 properties. So, first of all, if I have a positive instance, there must be a proof that gets accepted with probability 1, meaning always. And if it's a negative instance, there is no proof that is good enough in the sense of epsilon. So there is no proof that that can convince the verifier with certainty bigger than epsilon that the proof is actually correct. Well, this is one of the way to phrase the theorem. I actually somehow prefer the second way, which refers to approximation of the constraint satisfaction problem. So this inapproximability version is equivalent to the first one. You may see, like, it says that there exists positive epsilon bounded from 1 again, such that it is NP hard to distinguish positive instances of 3 sat from those where only epsilon fraction of constraints can be satisfied. So I took this phrasing from the paper of Dinur. So the surprising fact about this phrasing of the theorem is that it refers only to one problem in the class of NP, namely 3 sat. But on the other hand, if you think about it a little bit, it actually makes some sense, because 3 sat is a well-known NP complete problem, and as any other NP complete problem, every problem in the class NP can be reduced to 3 sat via a polynomial time reduction. So in some sense, you can exploit this polynomial time reduction in a way that instead of giving a proof for your original problem, you actually give a proof, you request a proof for the instance that is obtained by the polynomial time reduction to 3 sat. And this is exactly how you prove that the 2 versions are equivalent. So the other important thing about this phrasing of the theorem is that it somehow says that the PCP theorem is essentially a theorem about inapproximability of the constraint satisfaction problem. And this is how it's viewed in the proof of Dinur, and this is how I personally see it. And it allows you to use the technique that you know from other CSP problems. So what is a CSP? So CSP, the constraint satisfaction problem over an alphabet sigma, is a problem that on input gets an n tuple of variables and a list of constraints. Each of the constraints involves some k tuple of variables, and is of the form, this k tuple is in some prescribed relation. So when you are thinking about a verifier, right? So your variables are the bits, they can attain 2 values, 0 or 1. and the corresponding relation is the relation on which the verifier accepts on these bits. So it's the set of all triples of bits that get accepted. And the goal in the CSP is find an assignment of values from the alphabet sigma to all the variables, such that each of the constraints is satisfied, which is formally written in this way. The constraint satisfaction problem is in general NP complete. But what we usually do is we somehow restrict the relations that can appear in the constraints. There are many various restrictions, and you get concrete problems that you might know. The three-sat problem that I've already mentioned, so it is a domain on a Boolean alphabet with just 2 elements, and each of the relation is restricted to be of arity at most 3. So each of the relation corresponds to a bunch of clauses on the same triple of variables. You can express graph C coloring for any constant C just by taking a CSP with an alphabet of size C, and the relation is the inequality relation. Another CSP that plays quite a significant role in the general theory is so-called label cover. Label cover is just a CSP where each relation is of arity 2 and is actually given by is given as a graph of a function. So what I want to talk about in this part of the talk is some usage of the theorem. As I mentioned before, the theorem is essentially about approximation of CSP, and in fact it can be used to obtain a very good inapproximability of CSP. So this has been exposed in a paper of Hastad from 2001, who provided quite a few optimal inapproximability results about various CSPs. As an example, I put up this result about a 3-sat. So he claims that the PCP theorem is actually true for any epsilon as long as it's bigger than 7/8. So the 7/8 threshold comes from a very easy approximation algorithm to 3-sat, which just flips coins for each of the variables and assigns values at random. Then you have a probability of 7/8 that you satisfy any particular constraint of 3-sat. And so this result says that you cannot do better. You cannot do better. So this result of Hastad and many other similar results as this are obtained from the PCP theorem. And let me sketch briefly how the proof works. So in essence, you can start with the PCP theorem as I phrased it at the very beginning, knowing that it is NP hard to approximate 3-sat within some epsilon, very close to 1. And what you are trying to do is to lower the epsilon lower the epsilon as much as you can. So thankfully there is a method how to lower the epsilon. It's called parallel repetition. This is based on the theorem of Ras. That allows you to bring the epsilon as close to 0 as you want, but there is a price to pay for it. Namely that you have to change to a different CSP. You obtain the label cover problem, and moreover the alphabet of the CSP increases. As epsilon goes closer and closer to 0, this alphabet grows larger and larger. So you have to do some more work to get it back to your original CSP. And this is what Hastad devised in his paper. So he invented this framework of the long code and Fourier analysis that allows you to go from the label cover of very large alphabet back to your original CSP that you are interested in. And if you choose the parameters of this reduction right, you don't ruin the epsilon too much. So for this particular example, you can bring the epsilon as close to 7/8 as possible as you want. This essentially proves the theorem. So of course, like, there is a lot of things hidden in this second black box. Now, the same method can be applied also in the case of different CSPs, and one might say that most, or if not all, modern inapproximability results are basically built on this framework. Either there are direct application of this with better chosen parameters, or they are somehow generalizations of this. Now, let me get back to the proof of the PCP theorem, and I will talk about Dinurs proof of the PCP theorem. The Dinurs proof is currently considered to be the most elegant proof of the said theorem. So Dinur obtains the PCP theorem by a reduction from some NP-hard CSP. By first thinking about the CSP in the following way. So in CSP, you're supposed to distinguish between instances that are satisfiable from those that are not satisfiable. Well, not being satisfiable means that most, actually all but one constraints, at most all but one constraints can be satisfied. So this allows you to start with an epsilon that is 1 minus 1 over m, when m is the number of constraints. So this gives you a very small gap, and a gap that actually depends on the size of the instance. Dinur's approach is to gradually increase this gap and eventually make it independent of the size of the instance. And this is done in two steps. The first step reduces this epsilon, so amplifies the gap to some smaller epsilon. But on the other hand, there is again a price to pay, and the price to pay here is that the alphabet increases. So you have to do something else to bring it back to the beginning, and that is the second step, which is called alphabet reduction. The second step provides you the opposite trade-off. So you are decreasing the alphabet, but the price that you are paying is the epsilon. And if you choose the parameters right, if you choose your gap amplification right and the alphabet reduction right, you actually, by composing these two steps, you obtain something new. You overall amplify the gap without sacrificing the size of the alphabet. So, like in this example, you can make the gap 11 times bigger. And this is actually enough, because then you can just repeat the same process log m times. And if you control the parameters of the reductions right, you really obtain a polynomial time reduction. And after you compose it log m times, the epsilon will not be dependent on the number n, which is the number of constraints in your original instance, therefore obtaining the PCP theorem. So now, how do you do these two steps? That is the main question. And I will only talk about the alphabet reduction, though I must say that the key of the proof is actually in the gap amplification step. But the alphabet reduction is a necessary ingredient to make this whole idea work. So let's get to the alphabet reduction. The contribution of this paper is a new way how to make alphabet reduction. And actually, when I say new, it's not exactly new, because we are just stealing from other people. The idea here is, as you might have already thought from the way I'm presenting this, that what Hastad does in his proofs is essentially an alphabet reduction. So the question is, can we use the same? Can we use the same reduction in the proof of PCP of the PCP theorem for alphabet reduction? So the setting here is slightly different, but our answer is basically yes. You can do the same thing. Again, like you have to choose their parameters, right? But there is a lot of freedom. You can choose any CSP that you like. You are not bound to get your epsilon as low as you need to. You just need not to ruin it too much. What we do, we choose all these parameters so that the proof and the analysis is as simple as possible. And first of our choice is that we are not trying to prove an approximability of 3-sat. We are actually proving an approximability of a 4-array CSP with this relation R. This relation contains all tuples, all 4 tuples, except those where the first 2 entries are the same and the second 2 entries are the same. A good thing about this is that because of the arity, you can easily distribute the variables equally, and the second power of this relation is that it's really easy to analyze. In some way, it is way easier than any other Boolean relation. We further play with some other parameters to streamline the proof as much as possible, but there seems to be quite a lot of choice in what we do. So in particular, it seems to me that you can basically choose any fixed template CSP instead of this 4-array relation, and you have a lot of freedom how to devise your reduction, your gadget. Almost any reasonable choice will produce a result that is good enough, but it might be quite hard to analyze that it is indeed good enough. So our choice was make it as simple as possible, make the computations as simple as possible. And I will not show you the computations in this talk. I very much invite you to read the paper. I think it's much easier to follow computations when they are written on the paper than when I'm putting them here on my wall. And we tried to make the paper as approachable as possible. And we are not relying on any deep theory. So even from the analysis, Fourier analysis of Boolean functions, we only need very basic notions and very basic facts. Like, I think the most complicated one is Parseval's identity, which is quite easy to get. Another thing that I should mention is how our proof compares to other proofs of the alphabet reduction. So there is obviously a proof of alphabet reduction in Dinur's original paper, which is actually somehow convoluted. So it uses this 2-step reduction with 2 layers of error-correcting codes using something that is called an assignment tester. And frankly, I never understood what an assignment tester actually is. So please forgive me for not explaining it. So I believe that our paper is conceptually simpler, and because it is actually based on Hastad's technique, it is based on something that people already know about, or would need to learn about anyway, if they are interested in applying the PCP theorem. There is also another proof of alphabet reduction that was exposed in Radhakrishnan's and Sudan's reply to Dinur's proof of the PCP theorem. That is simpler, that is in a sense a gadget reduction similar to our paper, uses Hadamard codes, but we still believe that our proof is easier and more approachable. What should you take home from this talk? So my message is that the alphabet reduction is the easier part of Dinurs Proof. The essence of her argument lies in the gap amplification step, and alphabet reduction is a technical requirement that the proof needs, but it can be obtained via reasonably simple techniques. We failed to make it obvious, but I hope that we made it simple enough so that it can be presented. In fact, our reduction can be also seen as a simple gadget reduction, if you care about those, which is more important for people that work in the CSP theory, and it's quite important for people who work in the algebraic approach to CSP, because algebraic approach really classifies these simple gadget reductions, and it is known that it's not strong enough to explain consequences of the PCP theorem. So in this sense, alphabet reduction is trivial from that point of view. The other essential part of our message is that we are using basically the same techniques as Hastad. So if you want to learn some inapproximability theory, you just have to learn one set of skills, and namely this Hastad's technique and long codes and Fourier analysis of Boolean functions. And you can use this as well for the optimal inapproximability, which can be described as a low soundness regime, as well as in a high soundness regime of the PCP theorem. And the last part of my bit is that essentially, as well as with Hastad, so his technique is not restricted to one concrete CSP. It can be applied to many others. And in that sense, in our sketch, you are free to use any CSP that you want. And I see no trouble why any CSP that is NP complete couldn't be used in this reduction. So this might, in some sense, simplify the overall proof of inapproximability of a certain CSP in a way that you don't have to leave it too much. You can start with the blank CSP instance, for which you know that is not satisfiable, meaning one of the constraints is not satisfied. Then repeat gap amplification and alphabet reduction log n times. And when you get into the low soundness regime, just switch from gap amplification to parallel repetition, and just keep your alphabet reduction as you used it before to arrive to the optimal hardness. Okay, I think that's actually all from me now. So thank you for watching, and hope to see you at some future conference.